Okay, hello. There were three problems. I tried to bring it down to the bare minimum. 84, 94, and 107 from page 100. This is section 2.4. And, this was homework over the weekend. But I actually just forgot to... I meant to assign this midweek. If you're watching this on the day that I publish it or something, it's Monday. Hello, Analysis 1A. Last week we learned about the intermediate value theorem, very quickly, and then I forgot to assign homework on it, so I added it to over the weekend. There was already a lot of homework over the weekend. This might have gotten lost in the shuffle. So let's go over these problems right now. These problems are actually sort of really important. Well, I don't know about super important, but okay. Let's see. Number 84. What does it say? It says. There's a function, and the function is x squared plus 3x minus 2. And we're supposed to look at this function on the interval 0, 1. And the problem says, explain why the function has a 0 in the given interval. Okay, we did something like this, very much like this in class. How are you supposed to think about this? Well, okay, this is a polynomial. So first of all, let me just say that f is a polynomial, so f is continuous everywhere. All polynomials are continuous everywhere because all polynomials are just, they all have the property that the limit as x approaches a of a polynomial is its own value. Then that's just the definition of continuity. We showed that as an extension of the limit laws, or as an application of the limit laws. So since f is a polynomial, it's continuous everywhere. Sort of in particular, f is continuous on the closed interval 0, 1, because I'm supposed to be looking at this function on this interval 0, 1. Alright, well, let's take a closer look at this function. What is f of 0? Well, it's negative 2. And what is f of 1? Well, it's 2. Yeah, 4 minus 2 is 2. Alright, so kind of like there it is, right? At time 0, or at x equals 0, my function is negative 2. But when I get to 1, now my function is 2. And it's a polynomial, so it's continuous. So it means that my function must cross. I don't know where exactly, but it's the intermediate value theorem which tells me that my function must cross somewhere. And so now all we have to do, now we're just really just practicing writing this out. How do you invoke the intermediate value theorem? What does the intermediate value theorem say? It says that if you have some interval, and you have a continuous function on that interval, then if you suggest any y value whatsoever between the value at the beginning of the interval and the value at the end of the interval, then there must exist a point somewhere in that interval in which the function takes on that value. And in this case, the value that I'm proposing is 0. 0 is between negative 2 and 2, so somewhere on this interval the function must take on value 0. That's what the intermediate value theorem says. A function takes on every intermediate value. Okay, so we have already noted that this function is continuous on the interval 0, 1. You sort of need to write that down or something. And so, I'll even just say, since 0 is a y value, which is in between f of 0 and f of 1, because f of 1 is 2 and f of 0 is negative 2. So here I propose this intermediate value, 0, by the intermediate value theorem. What we know is that there exists some c on the interval 0, 1 such that f of c is 0. And that's what this problem is asking for. Explain why this function has a 0, has a root on this interval. Okay, that was kind of like just, I'll say that was just basically pre-calc. But now we're just using fancy words like intermediate value theorem. Okay, 94. Verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. Okay, so we have this function 94. What does this function look like? I don't know. X squared plus x over x minus 1. I suppose this is exactly the kind of thing that I'm really good at. What is this? X plus 1 over x minus 1. So I could, I suppose I could graph this function if I really wanted to. X squared plus x, if I divide by x minus 1, I get that it goes in x times. That's x squared minus x. That's 2x, so that's plus 2. See if I'm doing this right, who knows. That's probably right. So actually this function is x plus 2 plus 2 over x minus 1. Let's see, x squared plus x minus 2 plus 2. Yeah, that's just right. Okay, why am I doing all this? I don't know. -1, 0, 1. This is going to be cubicy, so minus plus minus plus, using all of my pre-calculus knowledge. But okay, let's start the calculus problem. The calculus problem says, hey, consider the interval 5/2, 4. And consider finding a place where f of c is 6. Alright, well, what do I know about this function? Let's see. I can just plug in 5/2 into this function, so let's do that. If I plug in 5/2, what do I get? This is slightly annoying. 25/4 and 5/2, so that's 25/4 and 5/2 would be 10/4, but that's all over 5/2 minus 1, so that's over 3/2. So I guess this is right. So this is 35/4 divided by 3/2, so like times 2/3, and indeed I get 35/6. Well, 35/6 is slightly less than 6. Fact. Next fact. What is f of 4? F of 4 is, well, this one should be a bit easier. 16 and 4 is 20 over 3. So I get 20 over 3. Well, that's just like 6 and 2/3, right? So that's just a little bit bigger than 6. So, is this function continuous on this interval? Yes. This is a rational function. A rational function is just the ratio of two polynomials. All polynomials are continuous everywhere. The ratio of two continuous functions is also continuous, except where the bottom function is undefined, so or is 0 rather. So yeah, this I can just look at this rational function, and by applying properties of continuity, I can say that that this function is continuous everywhere except at x equals 1. I'll even write that down. F is continuous everywhere except at x equals 1. That's just kind of a theorem about rational functions. So, what do we conclude? F is continuous on the relevant interval, this interval 5/2, 4. And so, what do I know? Well, I'm tempted now to sort of make an accurate graph of this function. Sort of don't want to, but maybe I should. X plus 2, so 1, 2, boom, boom. That's my slant asymptote. What else do I know about this function? Vertical asymptote at 1. That's probably just good enough for me. Doesn't cross the asymptote anywhere. I got sine charts, I got roots at 0 and -1. I've kind of like tricked myself into actually doing this now. This function is going to be negative, then positive, then negative, then positive. All right, so that's my function. That really wasn't too bad. But where all the action is happening, that's 1, that's 2, that's 3, that's 4. So if that's 2 here is 2.5. And it seems that So let me just kind of make this all work. So here at 2.5 I have a certain y value, boom. And here at 4 I have a certain y value, boom. And what are those y values? Well, I computed it kind of already, right? There at 2.5 I'm at this point here is 5 halves, comma, 35 sixths, so a little bit less than 6. But this other point here is 4, comma, 23rds, which is a little bit more than 6. And so there is, now I draw in the line y equals 6, and I see that focusing just on what's going on kind of on this interval here, I don't know how to do this exactly, but maybe I'll just make a big box or something, big red box. So just, look at what's happening inside this red rectangle. Well, inside this red rectangle, I have a continuous function, and at the beginning of the interval, at 5 halves, the value of the function is less than 6, but at the end of the interval, the value of the function is greater than 6. And so, the intermediate value theorem says that the function must be 6 somewhere. And that is really what's happening, right? This right here is 35 sixths. This right here is 23rds. And so, what we do is we say, since now the intermediate value that is being suggested is 6. And 6 really is an intermediate value because it's between f of 5 halves and f of 4. F of 4 we calculated to be 23rds, and f of 5 halves we calculated to be 35 sixths. So since this is true, and since the function is continuous on this interval, then this is exactly what the intermediate value theorem is designed for. Or since this is true, by the intermediate value theorem, there exists a point C on this interval 5 halves of 4 such that f of C is 6. Okay, so the intermediate value theorem sort of asserts that somewhere this function must be 6. Okay, and this is really, the whole problem is just meant for you to be comfortable with the intermediate value theorem and to know how to kind of cite it. A follow-up to this problem is, hey, find the actual value for which this is true. So in other words, let's not make this theoretical, let's actually do it. In other words, when is this function equal to 6? Okay, so now they're just kind of making me, solve this algebra problem or something. When is this function equal to 6? I guess that I can just do this. So that's x squared plus x equals 6x minus 6. So that's x squared minus 5x plus 6. That factors as minus 3 minus 2, x minus 2, x minus 3. So it's x squared, yep, and therefore there are 2 times when this function is going to equal 6. Notice that, okay, my graph isn't great, but it's not terrible either. There do appear to be 2 places at which this function is 6. Well, which of the ones is relevant to me? Answer 3, right? So the exact phrasing of the book's problem was, find the value of C guaranteed by the theorem. And the answer is that this one, right? C equals 3. 3 is the value of C guaranteed by the theorem. The theorem guarantees, the intermediate value theorem, that between 5 halves and 4, there is an x value for which the function is 6. And 3 is that x value. It's also true, by the way, that at x equals 2, this function is 6. But 2 is not the C guaranteed by the theorem because 2 is outside this interval, so 2 is just not under discussion. Okay, good. Maybe this is, I'm glad I kind of made this video because maybe this stuff is not totally obvious. All right, let's just do this last problem, 107, which is the mountain problem. And I've been teaching calculus for 13 years, and every year I've gone over this problem live, and it's kind of exciting and fun, and this is the first time ever that you're watching a video, so I hope you really are watching it, because it's kind of a fun problem to talk about live. It's an entire word problem, so to speak, and here's what it says. It's called déjà vu. And they went all out with the accents. I can't believe such a short word has so many dots on it. Déjà vu. At 8 a.m. on Saturday, a man begins running up the side of a mountain to his weekend campsite. On Sunday morning, at 8 a.m., he runs back down the mountain. See next page for figure. Figure, pretty useless. It takes him 20 minutes to run up, but only 10 minutes to run down. At some point on the way down, he realizes that he passed the same place at exactly the same time on Saturday. Prove that he is correct. Oh my gosh. What? Okay, so there's some kind of mountain. So let's draw the mountain. And you know, okay. So what's going on? Well, let's take notes, so to speak, using. Let's take notes. Okay, using pictures. At 8 a.m. on Saturday, the man begins running up the side of the mountain. So, okay, here is this person at 8 a.m. on Saturday. And what does he do? He runs up the mountain to his weekend campsite. Okay, it takes him 20 minutes to run up. So this is not a very big mountain. This is like a Maryland mountain. This is like, what's that mountain, Sugarloaf Mountain, or I think that's right, where you really can just run up it in 10 minutes, basically. So let's just note that it is at 8:20 a.m. On Saturday that he is up here on the top of the mountain. Kind of ran out of space a little bit, but all right, that's pretty good. So he's at the top of it, so it really does take him just 20 minutes to go up. And it's his weekend campsite, so he's camping up there. He stays up all night, and now he's going to go back down again. So it takes him on Sunday morning at 8 a.m., he's going to run down the mountain. Okay, so here he is, sort of still or something, up here at 8 a.m. on Sunday. And at 8 a.m. Sunday, he begins his descent. And for whatever reason, let's just say he goes back down the same path that he went up. And it takes him 10 minutes only. So by 8:10 a.m. on Sunday, he's back down again. All right, so this is kind of the idea, right? Starts at the bottom at 8 a.m. Saturday, takes 20 minutes to run up the mountain. Then 24 hours go by, basically. And at 8 a.m. Sunday, he runs down the mountain. It takes him 10 minutes, and he's at the bottom. Okay, so I think I get this now. At some point on the way down, he realizes that he passed the same place at exactly the same time on Saturday. In other words, it's like he's running up the mountain, and he has like a GoPro on or something like that, and he sees a pretty flower at 8:06 and 1 millisecond, and he hits the take a picture button or something. I don't know how GoPros work. And then 24 hours later, he's running back down the mountain, and he sees the exact same flower, and he also takes a picture, and he notices, hey, it's also exactly 8:06 and 1 millisecond. Okay, that's the idea of the problem. That's what they mean when they say, at some point on the way down, he realizes that he passed the same place at exactly the same time. Prove that he is correct. In other words, what we need to do right now is to prove that no matter what, if you follow back down again the exact same path that you followed up, then there will be a point somewhere along that path at which you were at that exact same point at that exact same time, by which we mean 24 hours earlier. Okay, how can we do this? Prove that this must happen. And then the book says, hey, here's a hint. And the hint just basically just tells you what to do. Let S of t and R of t be the position functions for the runs up and down the mountain. Okay, so S of t is going to be the run up, and R of t is going to be the run down. Okay, so let's turn this problem into sort of math by postulating, some functions which tell you sort of where you were along the path up and down the mountain. Okay, so let's just decide that this mountain is like, one, mountain unit high or something like that. And so what does this S of t function look like? Well, it's a position function. And it's a position function in which we start at 0 because this is the run up the mountain. So at time 0, I'm at the bottom. And at time 20, I'm at the top. And so I don't know the exact way in which we go up this mountain. I just know that we go up it. Assuming he doesn't do any backtracking or anything kind of silly like that, then after 20 minutes, he's up on the top. He goes from position 0 to position 1. And so this is kind of like time on the x-axis. This is minutes, and this is position, and the units are like mountain units, and we've defined this mountain to have height 1 mountain unit high. Okay, what does the down function look like? Well, it says, all right, we start here at 0, and now at 10, we're kind of already at the bottom. So now this is my position, but at time 0, which is to say at 8. This time is in minutes, and it's really like minutes past 8 a.m. of course. Okay, and my position function now begins at 1 because the guy's up at the top of the mountain, 8 a.m. on Sunday, and by the time we get to 10, we're already kind of back down again. And then he just chills over here for 10 more minutes, so he's sort of still on the ground. Okay, well, good. So what do we have here? We have two functions which kind of cross each other, right? I drew these on two separate graphs, but if you were to superimpose these graphs, which maybe is actually kind of a more reasonable thing to do, right? This is S. I'll do S now in blue, and I'll do like R in red or something. So this blue is S, and I shall now do R in red, sort of adding them to the same thing. Well, now, do you just agree that, of course, the answer is yes, these two curves intersect. And the point at which they intersect is a point at which the runner is at the exact same position, in other words, at the exact same height, at the exact same time. Because whatever this time is, where these curves R and S cross, is a time, is a number where he was at this exact same position at the exact same time. So actually this whole problem just reduces to showing that these two curves, R and S, must cross. But of course they must cross, because one starts high and the other one ends low, and the other one starts low and the other one ends high. Okay, so what does the intermediate value theorem have to do with this? Well, the intermediate value theorem says that, as we've been seeing, that a continuous function takes on every intermediate value. And so, it's very possible to simply just say, dude, these curves cross, because like, duh, and then the problem is just over. But you can actually prove that these two curves cross. How do I kind of know that these two curves cross? Well, I know that they cross because I know that the curves are continuous. S is the function describing the ascent of the mountain, and assuming the guy's not doing anything insane, his position will be a continuous function of the time elapsed. And the function R going down the mountain will also be continuous. So since these functions are continuous, there are no sort of like gaps or holes or infinite behavior or anything kind of insane like that. It's really the continuity of these two functions which ensures that they have to meet. And so the book says, hey, construct this new function, f, So let f of t be the difference between s of t and r of t. And this is like this kind of brilliant idea, which is going to come up several times in this course. When you want to prove that two functions are equal to each other, in fact what you do is you construct a new function, which is the difference of those two functions, and you show that that new function is 0 somewhere. Okay, and this is exactly what happened. This was the last problem from the packet, final assignment on limits. Assume that we had already done this, had this conversation before I assigned that problem. Oops. Well, anyway, what's the significance of this? The significance of this function, well, first of all, since s and r are continuous on the interval 0, 20, then so is f. And now we can see, okay, what is f of 0? Well, f of 0 is just s of 0 minus r of 0. What's s of 0? S of 0 is 0, and r of 0 is 1. And so this f function starts out at -1, and what is f of 20? It's s of 20 minus r of 20 by definition. What's s of 20? We're at the top of the mountain, and r of 20 is 0. And so this f function, if I were to make a picture of it, says that at time 0 I'm at -1, and at time 20 I'm at 1. So since this f function is continuous, then what I'm going to do is I'm going to apply the intermediate value theorem to f. And I'm going to say that somewhere f must be 0. And so we say, okay, since f is continuous, well, okay, f is continuous, now we say, all right, take the intermediate value 0, which is between f of 0 and f of 20, f of 20 being 1, and f of 0 being -1. Since this is true, then by the intermediate value theorem, there exists a c on the interval 0, 20 such that f of c equals 0. A function, continuous function, must take on every intermediate value. And here the intermediate value being proposed is 0. Okay, so if f of c is 0, but of course f of c is just, by the definition of f, s of c minus r of c, and if that's 0, then I've just proved that somewhere there must be some time c at which f of c and r of c are equal. And this time c that I just proved must exist is the time when the guy is in the exact same place at the exact same time. It's kind of plus 24 hours. Goodbye.